So welcome everyone. This is the last talk for our joint probability seminar, and then we come back in the 11th of August. So today it is our great pleasure to have Sabine Jansen from LMU Munich, and she will talk about intertwining and orthogonal polynomials for interfacing particles in RD. Sabine, when you want, you can start.
All right, so thank you very much for the invitation. There's an echo, no? I don't hear.
Now it's better.
Maybe people should mute themselves.
Yes.
Okay, let's try. So thank you very much for, now it's better. Thank you very much for the invitation and the opportunity to talk. So what I'm going to speak about is work where I would say it's still relatively early stage. So there are many things that I do not understand, and I will share my non-understanding in part. And I see that there's some experts in the audience, so please feel free to comment or intervene in the middle. All right. So what I'm going to talk about is very much motivated by a series of results on duality for interacting particle systems. And specifically works on duality by Chiara, and I also saw that Joya Carinci is in the audience, where you look at particle systems on a lattice, and you have duality functions that are somehow related to orthogonal polynomials or to falling factorials. So then the question was more trying to understand the structure of all these things. Can you formulate similar relations when the particles that you're interested in don't move on the lattice, but instead they happen to move in the continuum? And the challenge is, well, what would an orthogonal polynomial be in that case? And the nice, for me, mathematical surprise is that when you start digging and you start trying to understand what is the proper notions, you end up with beautiful connections with a completely different area of mathematics and probability, which is infinite dimensional analysis and chaos decompositions and multiple stochastic integrals. So I will try to convey a little bit the flavor of the connection that occurs. And as a warning, parts of the talk are going to be a little bit technical because it feels like it's hard to present these things in a light feeling way. All right, so now for outline, what I will try to do first is to clarify, okay, what is the configuration space and what kind of bookkeeping do I use for particle systems in the continuum? And what kind of Markov processes am I interested in? And I will use two guiding examples if you want. Number one is going to be independent particles. So every particle just moves independently according to some Markov dynamics. And if you like StatMech vocabulary, you could think of a free Kawasaki continuum version. And the other example is a continuum version of a symmetric inclusion process, which some of you know, and for the others, I will remind ourselves of what that is. So after that, I will say that, well, there's one intertwining relation, which in discrete setup has to do with falling factorials or binomial coefficients, which actually is the same or is related to a transformation which is called the K transform, and which had been introduced in the 70s by Lenard. And this doesn't have orthogonal polynomials yet. After that, I will try to recap some known things about orthogonal polynomials for Levy random fields, and then see how do I use these things in order to formulate a continuum version of unitary or orthogonal self-intertwining relations with orthogonal polynomials. And I should mention, well, the original title had duality. Actually, I will focus more on intertwining today. And I think because of time, I won't have time to explain how the two are related, but they are. All right, so let's start with what is a point configuration? Because that's already where sometimes conflicts start. Because some bookkeeping is loved by some groups of people and absolutely hated by others. So what is a point configuration? It's just a collection of points, x1, x2, xj, etc. And I want them to move, let's say, in RD to make things concrete. And I would like to have a bookkeeping where I say, well, I don't want to take into account how particles are labeled. So if I relabel and redistribute the indices, nothing should change. I do want to allow that multiple particles can sit at the same spot. And this I do want to allow in order to make a better connection with a lattice picture where I might think of having a lattice, and on each lattice side there might be a certain number of particles. Good. So one way of doing that is to say, well, instead of focusing on sets of labeled coordinates, you could just say, for every subregion B, you define a counting variable capital NB, which tells you how many variables sit or how many points are in that region. So then you just get family of occupation numbers. You can push the level of abstraction a little bit further and say, well, of course, if you have two regions, let's say A and B, and you ask what is the number of points in A union B, so what is N and XA union B, that's of course number of points in A plus number of points in B. So you recognize that there's a property of measure, and this you can take seriously and just say, well, I want to model my configuration by saying this is a counting measure. So it's a measure which might have infinite total mass. It is given by the sum of the Diracs. And to every subset B observation window of RD, it assigns an integer number or infinite, which is just the occupation number of that region, and which counts how many points sit in capital B. And so this is what I will use in order to define my notion of configuration space. It's going to be a space of counting measures, meaning spaces of finite or countable sums of Dirac measures. Two relevant subspaces would be locally finite configurations. So you might wish that every bounded region has finitely many points. Or you could even ask, so this is here NF, that perhaps you only want to look at configurations that have finitely many points in total. And then since we want to do probability, we need a sigma algebra. The sigma algebra, so this calligraphic N, is simply the smallest sigma algebra that turns all those occupation numbers with B, a bounded Borel set, into measurable groups. So that's configuration space. And just, I mean, it took me a while to get around to this bookkeeping in terms of measures. Because the disadvantage is then when you do probability, it means that you put a probability measure on a space of measures. And in the beginning, it feels unnecessarily complicated. I think it took me 1 or 2 years before I got around to it, and now I use it all the time. So just to convince yourself, okay, a little bit more argument. Of course, you could do all these things also, but it doesn't have to be RD. You could do it on ZD. And then it becomes quite natural because on a countable space, if you look, let's say, just at locally finite configurations, then you can just identify each configuration with a vector of integers, where nx just represents the number of particles that sits at site little nx. And this, of course, you could also view as a measure where you say the occupation number of region B is just the sum of all the small occupation numbers for lattice sites x and little. So it's very natural. It just takes some getting used to writing mu of capital. And doing so, you see that there's a one-to-one correspondence between vectors of integers and 0 to the ZD. And on the other side, locally finite configurations and ZD. And I've already said what little nx should be. Now, interacting particle systems. So very, very broadly, what we're going to be interested in is continuous time Markov processes whose state space I won't always be very clean on the distinction, is one of those configuration spaces. Maybe locally finite, most of the time actually finite. And these things, processes like that, they occur in many areas of application. So in statistical mechanics, you could think of Glauber birth and death processes. So instead of having spin flip like for easing, you would have birth of a particle or disappearance of a particle. You could look at Kawasaki particle hopping. So particles, points hop around. Models for transport for which you want to do hydrodynamic limits. I think most of you know these things much better than I do. There's also people looking from a completely different angle, coming from telecommunications. So there they think of the points as, let's say, agents with cell phones, and the cell phones might connect with each other, and then people are interested in connectivity properties of moving, evolving networks. You could also think of mathematical population genetics or theoretical ecology, where the points correspond, for example, to individuals of a population. Or, okay, maybe I should put this into parentheses, but there's also the topic, an area in random matrices where you look at interacting diffusions, and one keyword that comes up sometimes is Dyson-Brownian motion. And there the points are not, actually are eigenvalues of a time-dependent random matrix. So today I won't look at any of those complicated things, but something much simpler. And I will focus on processes that are consistent, I'll say what that means, and that conserve total particle number. So birth and death is out. And now the two examples I want you to have in mind. Number one is independent random walkers, or if you like, free Kawasaki. And this is constructed as follows. Suppose that you're given a family of independent Markov processes for a single particle dynamics, capital Xi. Then if you just forget about the information of the labeling and just look at the corresponding counting measure, then you obtain a process with state space, the configuration space introduced before. So if at time 0, your configuration eta consists of the points xi of 0, then your dynamics is such that at time t larger than 0, the configuration will simply consist of the points that have evolved according to the single particle dynamics. And each xi evolves independently. If your one particle dynamics happens to be a jump process with a jump kernel k of x dy, then the generator, and I'm saying formal because I'm not going into questions of domains and the like, the formal generator is given by this double integral, where the outer integral is an integral with respect to the counting measure. And that's something that's taking some getting used to. Whenever I write an integral with respect to a counting measure, you should really think of it as a summation over all particles of the configuration. So you have a summation over all particles of the configuration. Each particle can disappear. So it hops away from position x, and it jumps to position y, where the y is chosen according to this kernel k of x dy. Example number 2, that would be symmetric inclusion process. Let me try to draw a picture. I'm not good at these things. So the idea over here is that, well, you have a bunch of particles, and I want you to think of them as I'm drawing piles because I'm allowing multiple occupancy of a site. Okay, and the dynamics is such that what can happen is that a particle can depart from somewhere. And then what it does is that either it decides to join another pile, or it goes somewhere else and you have to say where. And the dynamics is going to be such that it likes to join big piles. So there is an attraction in it. So let me say what it does. Well, the formal generator, given a finite measure alpha, and I'm choosing it finite because I want to make my life easy. is given by this expression, which is very similar to what we just saw. But the difference is now that instead of having the jump kernel that we had before, you here have this thing that you have an alpha, this is the measure, and then you have here this plus eta, which tells you that you like to go where another particle already sits. If you think of the jump-hold construction of continuous time Markov processes, what you do over here is that you wait for an exponential time. When the time is over, you choose uniformly at random one of the n particles. So here I'm looking at the finitely many particle dynamics. And then the chosen particle, x equal xi, let's say, jumps to a new location. And it can do this in two ways corresponding to the alpha plus eta part up here, which is that either with a certain probability, it just joins the location of joins one of the existing locations. Or with another probability, you just go somewhere and you choose your target location according to the measure alpha, which is up there. And of course, you see over here, so this is one way you could twiddle a little bit and change this term up here by something where you could introduce a bit more spatial structure. I won't say much on where this process comes from. I think that people in the audience know better. One of the places where it appears is as a model that is dual to a model for energy transport. And there it is actually on the lattice, and there it is actually used. There are also connections with mathematical biology. I stop here. Good. So that's kind of the setup. And now let me come to the first block of results, which is where I want to say how Lenard's K transform intertwines a dynamics. And first I should say, well, I've written consistency, consistent process. This holds not only for the two processes that I wrote down before, but for a bigger class of processes. And I'm using a notion of consistency, which informally means the following. A process is consistent if the following two steps commute. Number one, time evolve a configuration. And number two, remove a point chosen uniformly at random among the points. And it shouldn't matter in which order you perform those steps. Now, to make that a bit more formal and to write down something that you could apply if you wanted to infinitely many points. See, the step number two is a bit problematic in that case. You can introduce an operation, which I call an annihilation operation, which maps a function from configuration space, let's say non-negative, to a new function AF. And I wrote down three expressions. Number one is this abstract way of writing it, where you write an integral with respect to a counting measure. Now remember, integral with respect to a counting measure is really a sum over location of particles. So what this means is that new function evaluated in the configuration of points I is simply you sum over all points of the configurations, and then you evaluate your function in a new configuration where you simply have deleted the particle that you chose in your sums. Or even more concretely over here, you see if you do it for n points, 1 over n AF configuration of n points x1 to xn is simply 1 over n. You choose, this is like choosing randomly among the n particles. And then you evaluate your function in a configuration where you have crossed out and deleted particle number. And our consistency simply means that your transition function PT, or semi-group if you prefer, commutes with this annihilation operator. And I also want to assume that the dynamics is conservative, meaning that the total particle number always stays the same. No birth and no death. And also I think, yeah, to stay on the safe side, most of the time everything will happen in spaces of finitely many configurations. And this notion of consistency, while examples are independent random walkers or free Kawasaki, there's also something for those of you who know, the so-called Howard-Warren flow of sticky Brownian motions. Actually, these first two examples satisfy a stronger notion of consistency, which has been introduced in the context of stochastic flows of kernels and mappings by Leland and Resumo, I think, mostly studied.
Yeah, there is a question.
I was.
Okay.
Sabine, there is a question from Milton.
Yes, please.
Hi.
Milton.
Yeah, so I have a question that's so I'm slightly more used to the following notion of consistent from the world of particle systems on ZD, which is that what you do is that at the beginning you tag a particle, and you see where this particle goes, and at the end you erase it, and that's the procedure which has to be commutative, no? Which has to be the same as erasing the particle at the beginning and then let the dynamics go. I understand that here, so it seems that this notion that you're introducing is weaker than that, because the idea is that if you choose it uniformly at random, you don't really need to tag a particle, no? But I don't know if it's really weaker or just.
I would like to say that it is weaker, but I would need to check.
Okay.
But I agree. But that's good. I didn't think of that connection. Yes. So if I have labeled particles, then for sure this property of consistency it asks less of the process than to say you just remove one labeled particle.
Yeah.
Yeah. But in these first two examples, I mean, for independent random walkers, of course, you also have consistency in the stronger sense.
Yeah.
Yeah.
Thank you.
Okay. And so, of course, this notion, I mean, we didn't invent it. It comes from other people's work. All right. It's just this extends without any problems to the continuum. So now Lenard's K transform. This is a very classical object, but I learned about it only quite recently when I tried to understand in statistical mechanics something. So given a map from the space of finite configurations to the non-negative reals, you define a new function kf, which is defined as follows. If you evaluate kf in a configuration made of possibly infinitely many particles xi, then this is given by a function of empty configuration plus summation number of particles 1 over n factorial, and then you sum over all ordered tuples of pairwise distinct indices, and you evaluate a function and you have all the n tuple contributions. So this is designed to be an abstract form of, well, very often you might be interested, for example, in something like a total energy, which might be a sum of pairwise contributions, right? And then you would just decide to write this as the K transform of a function that happens to live on n equal 2. So this is one way of formalizing functions that are given as sums over pairs, triplets, n tuples, etc. This was introduced, I think, on the name capital S by Lenard in 1975 in order to study correlation functions in a systematic way. And the relation with correlation functions is that if I have a random process eta, point process, and I evaluate what is kf of eta, it turns out to be given by a sum where you have the correlation function set. That's just a very quick parenthesis. And now comes the theorem, which generalizes a similar result by Carinci, Giardina, and Riedich on the lattice, except that they prove equivalence and we have only one direction, is that if I have a process living on finite configuration that is conservative and consistent, then the K transform intertwines the dynamics, meaning that PTK is the same as KPT. And I should say that even in the continuum for free Kawasaki dynamics, this was known. I don't know if Kondratiev, Kuna, Oliveira da Silva, and Streiter, this is the first, but this is where I found it. And what is nice about this thing is that what you get out of it is that the time evolution of the K particle correlation function of a many-body system happens to be completely determined by the K particle time evolution. And that is a nice thing, because if you, depending on what is your context, maybe the keyword of VBGKY hierarchy rings a bell. So here, this is a situation where there is no complicated hierarchy. If you want to know how does the two-point function evolve, you only need to know how does your dynamics act on two particles. Now, let me skip the details on how that works and instead show you a slide that connects it a bit better to what happens in the discrete world. Well, what would happen if I were to put these things back not on RD, but on ZD? And remember, locally finite configurations, in that case, it's just vectors of non-negative integers telling you how many particles sit at a given lattice site. Then what is K? Well, it's a linear map from functions to functions. So there's a matrix that goes with it. And it turns out that you can do a little bit of combinatorics. And remember that there were these n tuples and things like that. And you find that the matrix of the K transform is simply given by a product of binomials, which may or may not make it look more concrete. But this is precisely an intertwining matrix, which appeared in the work on a lattice. And this is how one can understand that this allows you to generalize lattice results. And this is what I wanted to say about the K transform. Any questions on that?
So in a sense, it plays the role of the duality function.
Yes.
In a sense.
It is.
Okay.
I mean, in order to get the duality function, you would have to divide by the reversible measure. It is what you use in order to act on the cheap duality function.
Okay, thank you.
That was the part that I had to evacuate, yes. All right. So now to the next one about orthogonal polynomials. And this is where I try to recap what I have understood. It's still a bit shaky about things that I know. But before I do that, let me say what kind of thing we're trying to generalize. And it is motivated by results on lattice systems by Chiara and Christian Giardina and by Frank Riedich and Federico Sau. So what happens is that there are several or many interacting particle systems on lattices that happen to have factorized reversible measures, namely measures which on n0 to the zd just happen to be product measures, where in the shift invariant case, you just say take the same measure all again. Also, what the structure that appears is that often there are self-duality functions that have a certain product form. So you have functions of two infinite vectors that are simply given as products. And all but finitely many of these terms here are equal to 1, so the infinite product is well defined. And on top of that, the function that appears there is given in terms of some kind of discrete orthogonal polynomial, perhaps divided here by the reversible measure. Now, I can't tell you why this is interesting, but that's what our starting point was and what we try to generalize. So the question is, what about continuum versions? And what I want to do in the recap, where I summarize what is known, is to see, well, how do some of these discrete ingredients translate into the continuum? The first observation is that the analog of these factorized measures mu just become infinitely divisible fields, or Levy fields, or compound Poisson, whichever name you prefer. And then for orthogonal polynomials, so 3 references that I found very useful was a book by Schoutens on orthogonal polynomials and stochastic processes. There's a paper by Nualard and Schoutens about chaotic and predictable representations for Levy processes, and a paper by Eugene Litvinov about orthogonal decompositions for Levy processes with an application to Gamma, Pascal, and Maxwell processes. And I would say that we're still in the process of understanding these things. All right. So let me first try to say what is a Levy point process or compound Poisson. So the input is a locally finite measure alpha. Let's just make our life easy and say it is finite. And I think most of the time I will assume that it is diffuse, so, or atom free. So alpha of every singleton is just 0. And then I also give myself a family of probability weights m of k on the non-zero natural integers. And then I want to look at the unique probability measure p on the space of configurations. If alpha is finite, it lives on the finite configurations, such that if I take a random variable with log p, then the Laplace functional is given by a certain form. So first, what is the Laplace functional of a random point configuration? Is a functional which maps a non-negative test function f to the expected value of e to the minus integral f d eta. And you ask that this is of this form, explicit form given on the right-hand side, where you have the exponential of the integral over Rd, sum over k. Then there's this term e to the minus k f of x minus 1. Remember, f is a test function. It's a variable of a Laplace functional. The integer k is summed out against the m of k, and the x variable is integrated out against alpha of dx. Now, I hope that this formula rings a bell with you. So either in the simplest case, I hope you, but might remind you of the Laplace functional, Laplace transform of a Poisson random variable, right? That would not have a k over here. A bit further, you might think of Ledy processes and Ledy triplets without Brownian part. And that is what you should have. Now, connecting it back to the two guiding examples, if I just choose m of k to be equal to 1 if k is equal 1 and 0 else, so the only contribution over here would be k equal 1, then the p or the eta just happens to be a Poisson point process with intensity measured outcome. And if you prefer to think in terms of stochastic of time evolutions, you should think of this as a stationary measure for free Kawasaki under the condition that the intensity measure alpha is invariant with respect to the one particle dynamics. Now, what kind of properties does this have? And also, maybe not everyone knows what a Poisson process is. So the two key properties are the following. If I choose observation windows, B1 to Bn, that are disjoint, and I just look at number of particles in distinct regions, then those happen to be independent random variables. And now you should connect this mentally to this factorized form or product form of the measure mu in the lattice case. The other property is that eta of b, so the number of particles in a region, is an infinitely divisible or an compound Poisson random variable. And in the example 1, the number of points in a region B would simply be a Poisson random variable with parameter intensity measure of observation window. The other example, remember, the other guiding example was the inclusion process, where you have this attractive component. This corresponds to choosing a parameter little p, so this is an additional parameter. I make a choice, I make this choice of m of k, just falls from the sky, but let's just accept this. And then what happens is that it's a little bit like a Poisson process up there, but now the number of points in a region B happens to be a negative binomial random variable. With parameters, well, there's the p that enters, and there's a parameter again given by intensity measure of observation window p. And there's this concrete formula which tells you what is the probability of seeing endpoints in capital. And such a random point configuration is often called a Pascal point process. Right. Terminology we got from the Schouten's book, among others. And this happens to be, so this I don't know if this was known, I think this is actually new, in the continuum at least, it happens to be a reversible measure for the symmetric inclusion process. Okay, so you are in a situation that you look at a process which is consistent, and it has a reversible measure which happens to be infinitely divisible, and that's good. Good. So this was the analog of the factorized measure. Now, what about polynomials? So let's fix the law capital P, probability measure. Let's work in the Hilbert space A. Okay, I think later on I'm going to use H for something different, so let me just cross this out. So let's just work in the corresponding L2 space with respect to this measure capital P. And let me use the notation eta of f. That's just the integral over Rd f against eta. And remember, whenever I integrate against a counting measure, that's really a sum over all the particles of the configuration. So then I want to look at this closure Pn and think of it as polynomials of degree smaller or equal to n, which would be the closure in the L2 space of linear combinations of maps where a point configuration is mapped to a product eta f1 all the way up to eta fk, where f1 to fk are supposed to be nice test functions and k is smaller or equal to n. On a lattice, what would this be? Well, on a lattice, this would simply be a sum over x1 to xk, k tuples of lattice sites, some coefficient which depends on the x, and then that's the main thing. You have over here the products of the occupation numbers associated to those lattice sites. So you see, this is a polynomial of degree k smaller or equal to n in the occupation numbers. And that's a non-fancy way of accepting why I would call this a polynomial. There are, I think, more abstract and more mathematical ways, but that does the trick for now. These are polynomials. So now what about orthogonal polynomials? Well, you would like to have polynomials that are such that everything that is of degree n should be orthogonal to everything that is of degree small or equal to n minus 1. So you can try to do that by doing some kind of Gram-Schmidt orthogonalization procedure. And let me be a bit quick over here. So I define a space boldface P index n, which is the orthogonal complement of the sum of the degree small or equal n minus 1 polynomials in Pn. And what that means is that those spaces are not now going to be orthogonal. And the degree small or equal to n polynomial closure is simply the sum of those orthogonal polynomials. And then there's a notation which those of you who have some quantum exposure might recognize. There it often stands for Wick ordering. So I take the polynomial eta f1 to eta fn. And now I put these columns to the left and to the right. And what this is supposed to mean is that you take the orthogonal projection of what is inside onto the space capital Pn. Now that sounds horribly abstract, but it turns out that this is how you can relate polynomials to univariate orthogonal polynomials. Because for example, example 1, if you work in the Poisson setup, so remember, there's a choice of the underlying probability measure because you look at an L2 space with respect to probability measure. If you take a polynomial on the left side, which is simply given by, okay, you take A1 to AK, disjoint regions of Rd, so those are just observation windows, and you take integers N1, n2, etc., summing up to a given n. And then I look at the polynomial, which is number of particles in a1 to the power n1, product dot 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 number of particles in ak to the power nk. I take the big ordered version of that, or the orthogonal projection, then this turns out to be a product of univariate orthogonal polynomials. In this case, they are called the Charlier polynomials, where you see the degree. So the variable of your polynomial corresponds to the number of particles in a given region. There's a parameter over here which refers to what kind of Poisson measure are those polynomials going to be orthogonal with respect to. And then there's the degree of the polynomial, which comes from the exponent over there. So you see, for certain choices of the test functions up here, you recover something which is simply a product of univariate orthogonal polynomials. And this is how, again, how you connect things to the lattice result. That's example 1. Example 2, if I choose from a measure for the L2 space that I'm looking at, not Poisson, but this stationary measure of the symmetric inclusion process, then instead what I get is a product of univariate maximum polynomials. And again, this is how it should be in light of what we know on the lattice. Good. So Chiara, how much time do I have? 5 or 10 minutes?
Yeah, you have.
Okay, good. So I need 2 more things. And again, yeah, so I need 2 more things. Now we have the orthogonal polynomials, but remember what I also wanted, I would like to write an equation which is a little bit like this intertwining relation we had for the K transform. So for the K transform, I wrote something which was PTK is equal to KPT. And now I want to replace the K by something else, which is going to be a unitary operator U. And the unitarity reflects the orthogonality of the orthogonal polynomials. So the way this works, or one way of setting it up, let me start with a Poisson world. In the Poisson world, you introduce another Hilbert space, which I called H, which is not what I had before, which is a Hilbert space of sequences Fn, where F0 is just a scalar. Fn is a function of n variables in Rd, square integrable with respect to the nth power or nth product of the intensity measure alpha, and symmetric, meaning it doesn't change if you change the order of the variables. And the norm in this Hilbert space is given by this expression over here, where you just take the sum of the squared norms of the individual Fn's in the corresponding L2 space. And then you put a 1 over n factorial. Well, this is a choice that makes some formulas pretty. Again, if some of you have had quantum exposure, that should be very familiar, even though you might be a little bit annoyed about this 1 over n factorial, which doesn't matter that much. And then, okay, here you shouldn't trust me to, okay, let me first say. So then the theorem is that, and this is a well-known thing, is that you have a unitary isomorphism between the Fock space, which is the space of sequences, and the L2 space on configuration space with respect to this Poisson measure. And roughly, modulo symmetrization, and don't trust me too much, there might be n factorials that floating around. Modulo symmetrization, you map a product, symmetrized tensor product of single variable functions fi to the corresponding orthogonalized polynomial in the L2 space. And so what this unitary does is that it maps functions of n variables, so that would be an Fn thing, to an orthogonal polynomial of degree n. And I won't go further, but this is the picture that people have in mind when there's the keyword of chaos decomposition. Now, when you look at the Pascal point process, things are a bit different. So something are the same, something are different. So basically, you have the same relation and a similar unitary isomorphism, but the difference is that you have to replace. So instead of looking at L2 spaces with respect to n product measure of the intensity measure, you have to choose some more complicated measure lambda n, which I won't go into how it is defined. The thing that I want to mention, and I don't know if this is new, I mean, we found it out on our own and we haven't seen it in the literature, but as I said, we're still exploring, is that you can also think of those lambda n's as the Janussi measures up to a factor of the original process. So it so happens that if I want to know what is the integral of a function of a configuration against the measure p, then up to a proportionality constant, you can compute it by looking at integrals against those measures lambda n. And let me be very quick and just say that the consequence of this is that this complicated extended Fock space happens to be unitarily equivalent in a very easy way to just the same original L2 space for finitely many particles. Good. So these were all the inputs, and now let me state what comes out of it and wake you up in case I lost you with the technicalities. So now comes the unitary intertwine. Let me first mention that, again, there are many things that are known. So for independent random walkers, free Kawasaki, where the one particle dynamics has a reversible measure alpha, one does know already that the unitary U, which maps the Fock space or original L2 space to the L2 space, is actually an intertwiner of the dynamics. And a classical reference is Surgailis, so it's Lithuanian, 1984. So now the question is, do you also have something like this more generally for our guiding example number 2? And the answer is yes. So if you take a finite diffuse measure and some parameter, you take P, the distribution of this Pascal point process, reversible measure of inclusion process. You look at the semi-group of the inclusion process, which is going to live on finite configurations. And I want to make a statement which is purely about semi-groups in L2 spaces. And I also take the labeled particle version, which acts in the Fock space, but really, if you want to just remember that this is basically the same as L2 NFP. It's just, do you want to do labeled stuff or not? And then what happens is that, okay, the measure is reversible and the unitary is indeed an intertwine. And this, for the inclusion process, is a continuum version of statements that have been proven before on the lattice. And you see, in order to formulate it, we needed a little bit of machinery. Okay, so that's what I wanted to say. So let me summarize. So the conclusion is that for consistent processes and conservative, Lenard's K-transform provides self-intertwining relations. And then there was a second statement, which is less general, so far I have formulated it in the talk only for independent random walkers and for the inclusion process, is that you can define a unitary intertwiner with orthogonal polynomials. And the orthogonal polynomials that you need have been introduced in the literature before. And then, of course, there's many things that you could still do. So some things we actually already did, which is, what about the algebraic approach? Well, you can do things algebraically, and you can do this whole game of SU11 algebra, raising and lowering operators. And specifically, Chiara, in your article, there's one theorem where you have a Baker-Campbell-Hausdorff formula that you use. this is also possible to do it in the continuum. So this we did, at least we understood the broad strokes. There's still some technicalities. Of course, you can ask, I mean, here I focused about independent random walkers and inclusion process. Can you do it more generally? So could you do consistent conservative processes that have other Levy reversible measures? Yeah, to be clarified. Then there's another question I would be curious about: classification of consistent processes. And that is because I also know consistency from a different topic, which is in the book by Pittman on combinatorial stochastic processes, where people look at partition value processes. And there's a notion of consistency, and then there are classification theorems, and there's Kingman coalescent, and there's Bolthausen-Smithman coalescent, and I wonder if something can be done for particles as well. And of course, well, we have some theorems just to make our life easy, and with finite alpha, that the full power, I would say, of these chaos decomposition and Fock space isomorphisms is actually when you have infinitely many particles. So what can you do there? And finally, what kind of nice theorems could you prove using those dualities and intertwining relations? So this for me is a big question mark, because I've never really worked on these things, but it shouldn't be absent from the outlook list. All right, thank you very much.
Thank you very much, Sabine, for this nice talk. Maybe we can unmute ourselves and clap our hands. Okay, are there any questions or comments?
Well, I have a question. So could you comment more about the application? So where would you like to apply this theory which you just presented on the one hand, and on the other hand, well, that reminds me about non-gradient hydrodynamical limit, in which you decompose your space in these orthogonal subspaces, and then you check whether the generator will apply smoothly on these spaces, so that there is a piece of the generator which keeps, say, the degrees, so keeps functions in the space to the same space, and then a piece which either increase or decrease the degree. And if you can control that in terms of the one which keeps the degree, you can prove. So did you look at these type of questions? So how the generator apply on these spaces? And
no, we haven't. I mean, we haven't investigated applications at all for now. And I have to say that I have never worked with duality. So I wouldn't really, I'm afraid I have to pass on this question. But maybe, Chiara, you have an idea how these things are applied in lattice.
Okay, for non-gradient system, I don't know, because, so, okay, a question that I have is that you can always state your last theorem also for exclusion, right? Okay.
I don't know how to define exclusion in the continuum, but...
Okay, but it's a problem to define the generator in the same way you did for inclusion?
Well, if you imagine particles jumping in the continuum, right, then somehow they're always going to miss each other. So it's not clear what the exclusion condition should look like.
I see.
So this we don't know yet how to do. Yeah, no, so applications we still have to think from scratch, I think. I was wondering, so these chaos decompositions, etc., people in spatial stochastic geometry and spatial statistics, they like using these things in order to define, to prove central limit theorems. And I was wondering, but that's extremely speculative, if it has any applications when you want to deal with fluctuation fields in hydrodynamic limits. Because in the time-independent case, I think that's a little bit what people have in mind, why they do those chaos decompositions. And I wonder if this can be somehow pushed, but I'm not really qualified to say anything more.
Okay, well, thanks for the very nice talking.
So maybe maybe Joya can say something, but I think if there is a duality the relation, then it suggests that the system is gradient and it conserves. So it doesn't have this extra. It closes the correlations. It doesn't increase the degree, but I don't know. Are there any more questions? Comments?
May I ask a question?
Mm-hmm.
So my question is about the infinitely many particles, because usually the way in which these infinitely many particles are constructed is that well, you construct a system with finite number of particles, and then you take the limit, no? And when you take the limit, what is important is to find some a priori bound that does not depend on the number of particles. So here, with these functions, now these duality functions type of things, you can actually get this a priori bound. So I was wondering whether it's if there is what are the difficulties to try when you try to do infinitely many particles?
I wouldn't expect that there's any difficulty. It's just that we wanted to focus on. So I agree. Let me first go to the slides where you have the time evolution. Oh yes, so that was what I did not tell you precisely. So I think in order to define, I agree that, I mean, what you can always do is that you know how the n particle dynamics should evolve, the correlation functions. And then the only bit that is missing in order to have existence of to lift this to an evolution in a proper Markov sense is that you need to say that the moment problem that associates probability measure with the correlation measures has a unique solution. So there you're saying that you're optimistic that the moment bounds that you need would automatically hold true. This I'm happy to believe, but I think I would need to see. And then, to be honest, I wouldn't expect any big difficulty. I just think that you have to be a bit more careful in some of the formalism. So somehow we derived relations and we did proofs which kind of use the alpha, and I think we would need to do use finiteness, and we would need to revisit some fine print. Okay, sorry, this was a little bit vague, but the short answer is I don't expect big problems.
Okay, thank you.
Are there any more questions?
Hi, I had a question.
Hi, Jeff.
So the internet might have cut out. So could you explain again what the issue is with defining exclusion on the continuum?
Well, the thing is, if you imagine that you have stuff that really moves continuously, if I remember what is exclusion process is that you want to forbid a jump in case your particle jumps to a location that is already occupied.
Right, yeah.
But suppose that your jump kernel K is absolutely continuous with respect to Lebesgue.
Oh, I see, yeah.
Exactly.
Okay. All right. Yeah, because I've heard Dyson-Brownian motion being described as the continuum analog of ASAP. But yeah, no, I see what your point is. Yeah, thanks.
Yeah. Well, that's interesting to keep in mind. Thank you.
Yeah. Thanks.
Are there more questions? Okay, so if not, let's thanks Sabine again. Okay, and we continue in August, I guess. Everyone have a nice vacation. Okay, bye-bye.
Bye-bye.
Bye-bye. Thank you.
Bye, Sabine. Thank you.
Bye, thanks.
Bye, Claudia.